goes through a step-down gearbox, which steps the speed down to 1800 RPM, which then spins a generator, which is basically just a giant electromagnet that spins and then produces the electricity at 13,800 volts, which we put out to a substation in the back, which you can't really see at this point in time. But it then goes to a couple step-up transformers that step that back up to 138,000 volts for distribution around town. The Holland BPW owns and operates 24 miles of transmission loop around the city of Holland at 138 kV or 138,000 volts, and that's what goes around the city in a giant loop. One for redundancy, and two just to get it to all the different substations in different neighborhoods and locations around town. Back in the plant, after we make the 50 megawatts with each gas turbine, that leaves the exhaust coming out of the backside at about 1100 degrees Fahrenheit. That's really hot. There's a lot of energy there, so we recuperate that in what we call a heat recovery steam generator. It basically takes that hot exhaust and puts it through a giant box that has tubes hanging down from the ceiling inside of it in the gas path. It's so dense with tubes, and they're finned tubes. We'll get a chance to look at some when we go out into the plant. The finned tubes actually hang down, and the hot exhaust gas goes past those where the heat transfers into the water that's inside the tubes, and it boils that water, preheats it. There's different zones. Some zones preheat, some zones have steam in them where it's superheating that steam. Some are what's called a generating tube where they're actually having the steam bubbles happen and you're actually making the steam inside the tube. We collect that steam up at the top on a steam drum. The steam there leaves the heat recovery steam generator and goes into that giant pipe rack that you saw, and then heads down the turbine deck to the steam turbine generator, which takes that high pressure, high temperature steam and runs it through a series of stationary and rotating blades to recoup that the heat energy that's in the steam and make it into mechanical energy. Our steam turbine spins at 4,400 RPM and then again goes to a step-down gearbox, which takes the speed down to 1,800 RPM to run the generator. Interesting fact about the 1,800 RPM machine is it's a 4-pole generator, so the electromagnet has a north, a south, and then another north and south. So our James Young plant just had the more common 2-pole, so they spun at 3,600 RPM, with just a north and a south pole for the electrical guys in here. So it's our first time for the Holland BPW operating a 4-pole machine. Really haven't noticed any difference other than it spins slower. So once the steam has gone through the steam turbine and all the energy's been taken out of it, or most of the energy's been taken out of it, out the backside of the steam turbine you end up with cold, wet steam that you can't pump. So steam doesn't pump real well, so we have to turn it back into water, so we condense that steam in a condenser. That's what we use this giant cooling tower for and our Snowmelt system for. So cold water gets pumped from those at a rate of 34,000 gallons a minute into the condenser, and in the condenser the cooling water goes through one side of the tube and the steam is on the outside of those tubes. It hits those tubes, condenses, turns back into, has a phase change and basically turns back into water, rains down into a pan in the bottom that we call the hot well. In the meanwhile, the heat that came out of that steam as part of the phase change then goes back around into the circulating water, which is then heated up, and that circulating water that leaves there at about 95 degrees Fahrenheit either goes back to the cooling tower or to Snowmelt, where it goes to some Snowmelt pumps and we pump it downtown at a rate of about 66 to 7,000 gallons a minute. So it's a pretty good pumping rate. It's about a 400 horsepower pump that we're running just to run Snowmelt and pump that downtown. Those pumps pump it downtown. It goes through all the little pipes and tubes, and it's just basically a giant heat exchanger for the streets downtown. That water comes back to this site and then dumps right into what we call the cooling tower basin. It's a giant Olympic-sized pond underneath the cooling tower. The balance of the water, the other 28,000 gallons that's part of our circulating water system, is actually going back to the cooling tower where it goes up the green pipes on the side. I don't know if you guys looked at that earlier. But the green pipes are called cooling tower risers. The water goes up and it goes through a series of pipes that basically distribute the water evenly over the whole surface area of the cooling tower and then sprinkles it down. And up on top there's a fan. So it's basically a cross flow evaporative cooler. So as the water's raining down, there's air being drawn up past it the opposite direction, and that causes evaporation, and evaporation causes cooling. So that water is then cooled back down. We see about a 20 to 30 degree drop in temperature from the cooling tower. The water rains back down into the basin, much colder, so it comes back at about 70 to 80 degrees, depending on the day, the temperature, how hard we're running Snowmelt, what the load is on the steam turbine. It goes through two pumps that are inside there. They're large 4,160 volt pumps, pumping at 34,000 gallons a minute again, pushing it right back to the steam turbine. So, yeah.
Why is it that you want to cool it down in the first place?
So that when you take the wet steam and you convert it back into water, you have to take heat out of that steam. So you end up with hot water. And what would happen is if you just didn't do anything and just kept cycling that water, you'd end up overheating that water and actually flashing it off and boiling it at some point, because the water would want to equalize to the temperature of the steam that's condensing on it. So we have to cool it down so that there's some reject place for that energy to go. That's a good question. Interesting thing about water in this plant, we're constantly cascading water. So the water, we actually take Holland City water at a rate of about 500 gallons a minute, 300 to 500 gallons a minute as our makeup water. That's how much we use all the time, 24/7. That water goes to making up the steam cycle. So the steam cycle is the boil, steam turbine, condense, pump it back into the boiler, it steams off again, and then it goes through the cycle again. You keep reusing that same water, but you can't constantly and forever use the same water. You have to change it, because otherwise the chemicals in it will cycle up and you'll get scaling on your boiler and you'll get bad water. So we have what's called a water treatment department here, where we actually demineralize water. We make super clean, super pure water. It's basically like a distilled water, but even more pure than what you get in the miner gun for distilled water. The water comes in from the Holland BPW water treatment plant, and we strip all the chlorines and all the other minerals off that are great for drinking, and we put it through a reverse osmosis system and then through some electric deionization polishers, and then it ends up in a giant tank. And we make that up at about 25 gallons a minute is what our typical makeup rate for water to the steam cycle is. The remainder of the water that comes into the plant is just going to make up for evaporative losses off the cooling tower. So you're evaporating so much water, that's the plume that you see off the top of the cooling tower. That's water evaporating that we have to then add back to the cycle. Talking about plume, a number of you have mentioned the Zeeland BPW, or not Zeeland BPW, but the Zeeland Consumers Energy Power Plant over in Zeeland that has fantastic railroad crossings that doesn't actually have a railroad. One thing that we did here with the construction of this power plant was we didn't want a plume. So we didn't want to ever have to put railroad crossing signs or police or close Chicago Drive, the main entryway to the town. So we purchased what was called a plume-abated cooling tower. That doesn't mean no plume, it means less plume. Our cooling tower, if you look at this one and then drive past the Zeeland one, you'll notice that ours is about twice as high. So where theirs kind of stops, they spread out the water, and then right above where they spread out the water, there's some fans that go up. Ours actually have a whole nother twice as tall length to them, because what we have is a heat exchanger that they have diagonal tubes that go through with louvers on the side that you'll see during the day, and those louvers actually take in dry air and they change the dew point of the vapor that's actually leaving that tower, and by moving that dew point you can actually change the range of which the visible plume is seen. So you're basically changing the humidity of the air so that on a given day and given temperatures you don't see the actual water that's coming out of the top of the tower. Now when you get to a really cold day like today, where it's in the 20s or in the teens, you're going to have a real hard time. It becomes a declining returns, or what's that called when you have law of diminishing returns. So you can spend a lot more money to get a wee little bit of gain on the cooling tower. It works in a certain range, So we spent as much money as we wanted to get down to a certain range of temperatures that was our average temperatures for the city of Holland. So on days when you get down into single digit temperatures, you'll still see a pretty good plume over here, but it's not, you know, half a mile or a mile long plume. It's, you know, 100, 200 yards or so from the tower, which doesn't hit Chicago Drive. So
Is that just for optics? I mean, is that so the town doesn't think that it's Homer Simpson and whatever?
Well, if you've ever driven by
people
the
think-
one in Zealand,
Yeah.
it shuts down the road.
Yeah.
Oh, so that's what you meant with the train?
Yeah, they literally
Yeah,
have.
so like all that ski going out just shuts visibility down to zero.
Yeah, you
So
can't-
you're
you can't-
shutting Chicago Drive down.
Yeah.
Got it.
Yep.
Okay, yeah, okay.
You
So
can't-
that's more than just cosmetic. Right?
Yeah, it's-
All right.
We didn't want the PR or the cosmetic issue here.
Gotcha.
So we didn't want, we wanted people to see the building, and we also didn't want to have the plume. Yeah.
Are the fans above that top section or between the two?
Nope, they're way up top. So the round shrouds on the top actually have some super fancy Netherlands made, ultra quiet, low speed fan blades. We wanted to be respectful of the neighbors. We have residents living right across the street, so we wanted no net change in the noise coming from this site. Self-imposed noise boundary that we didn't want any more noise coming from this site than what previously existed before we were here. So there's a berm out here around the cooling tower basin on the sides where the residents would be so that you can't hear the water falling and that noise. All of the panels inside the plant are acoustical rated so that you don't get any noise from the turbines or the gas valves or anything like that outside the plant. All the relief valves on the ceiling of the plant all have giant mufflers on them. And the cooling tower fans, which can be really weird if you get a higher speed fan that spins with a lot of blades, you'll get a chopping noise, and on certain days when there's an inversion layer, which is a certain type of cloud mass above the cooling tower, the sound will hit that and come right back down 100 yards, 500 yards, half a mile over, and then it'll shake somebody's house. So we didn't want any of that here, so low speed fans, super ultra quiet. They're pretty cool. They're carbon fiber. They have a really neat airfoil design to them. We really tried to be respectful of the neighbors and where we were putting the plant and how it looks. That all fed into it as part of the sustainable return on investment. So that's why you have a power plant that's got a big visitor center and a giant window so that passerbys can see inside the engine room, so to speak. It's kind of like an under the hood look when you're driving past. So that's kind of the basis of the design that they wanted.
Is this running right now? Like, are you at
Yeah, we're on line base load right now.
base load? So that's versus capacity. Is it?
They're probably making 130 megawatts right now.
Okay. All right. So this is what you would expect.
Yep.
This summer.
Yep.
I couldn't hear a thing from outside.
No.
I didn't notice it.
Being the plant engineer drives me nuts.
How do you know when it's broke?
At the young plant, I used to have an office right on the turbine deck, and so you'd sit there, and I knew we had a vibration problem when I started to have it on a turbine or a fan upstairs because my monitor would start to shake, and there was a personal mission to get that fixed because it was annoying me. You know, you could sit there and the floor would shake when you trip a unit because the stop valve would slam so hard that it'd shake the structure, and you'd be like, uh-oh, we just tripped, time to go to the control room. This one, you got nothing. Yeah.
Do your turbines float? I've heard of some of them that actually have some type of a floating mechanism, like a liquid bed or something.
Nope, ours don't have liquid beds. They are, all the turbines that we have are pinned from one central location. So these out here, the Siemens SGT 800 made in Finspång, Sweden, came with because of the temperatures, so I'll back up a little bit. Because of the temperatures, the steam turbine, or both the steam turbine and the combustion turbines will grow quite a bit. And because you've got bearings on either end of the machine that can cause alignment issues and vibration issues, you need to control that growth. So Siemens and General Electric on our GE turbines do a really good job of looking at the gaps in the